In this part of the course, we're going to describe the rotations of objects. Up till now, this is something we've completely ignored. In fact, we didn't really care what an object looked like at all. We could have just had it be a cube, a sphere, a perfect point, a cow, a human being, or a car. All we really cared about was that it was moving across a room and got from point A to point B. In other words, we described its linear motion. So it didn't matter if it was spinning around or changing orientation during all this time. All we really plotted was the vector of its center of gravity as it moved across a room. Now we're actually going to worry about the fact that the objects have some actual size and their shape, and that the thing might be moving in orientation as well as in direction. This is helpful to us because there are some problems that are more complicated, and because we think about the orientation of an object, we actually get to take advantage of that because it actually brings some new phenomena into play. So let's think about some examples. One is an easy one. You can think of a person diving off of a diving board. Initially, that person is standing straight up, feet down, head up. And as that person goes through linear motion, in other words, goes into a nice parabola under the force of gravity as that person's pulled down, at the same time, that person is also executing rotational motion because that person is going into a tuck, does a somersault, and is now head down as that person's about to splash into the water. So there's both linear motion there and rotational motion. So it's more complicated sometimes than just the parabolic motion under gravity. Sometimes rotational motion actually makes our life easier. We could describe the motion of the planets as they rotate around the sun using the equations of motion of velocity and acceleration, and it was really complicated because the position vector of that planet is constantly changing direction, and the velocity vector is constantly changing direction. The velocity vector here for Mercury might be heading into the page, but as it comes over here, it's heading out of the page. Well, if we choose to ignore that kind of way of describing it and think instead about rotations, we can think about Mercury sitting on the edge of a circle and always say that it's at some fixed radius on the edge of the circle, but just worry about what angle it's making around the circle, just like the hands on a clock. And so that's an easier way of describing the motion of Mercury. Even the fact that Mercury and all the other planets are spinning on their axes is actually easier to describe with rotations than with linear motion. If we thought about us as a little ant here on the surface of the Earth, describing our velocity and position vectors is really complicated because Earth is spinning around at the same time as it's going around the sun. But that's a really easy thing to describe if we just think about Earth as rotating, and we're always at some fixed distance from the center of the Earth. So sometimes actually rotations are easier. Other times rotations have a connection to linear motion that's really important for us to know about, and if we ignore that, then we're kind of missing out on something that's kind of important. That's very intuitive if you think about a bicycle. If the wheel doesn't rotate, then the bicycle doesn't move forward. And in fact, the amount that the wheel rotates around dictates how much the bicycle is going to move forward. So there's a connection there, and actually knowing that allows us to think about how much to pedal or how fast to pedal, because that tells us how to calculate how fast the bicycle will go. In fact, this rotation has an energy to it as well. Something that's spinning really fast has a lot of kinetic energy, and that would be complicated to describe with linear motion, but it's really easy to describe with rotational motion. And that energy is real enough that it gets converted into other forms of energy. You know that if you hit your brakes on a bike, the brake pads heat up, just like the brake pads on a car heat up if you slow down a car. And in fact, lots of people have thought about ways to make more efficient cars that recharge their batteries when you slow down by converting that energy back into electrical charge in the battery. So there's lots of things that are important to know about rotations and as how they can relate to energy conservation. There are other things that are just kind of cool to know about with rotations, and in fact they've allowed new things to be possible. Gyroscopes inside your iPhone are the things that allow you to know what direction your iPhone is facing at this moment in time. If you rotate your iPhone, you notice that the screen rotates with you. And that's only possible because there's a little gyroscope inside the iPhone, and it doesn't want to rotate. It wants to keep in the same orientation because of Newton's laws. Something that's rotating wants to keep rotating in the same fashion unless acted on by not a force, but something else called a torque. And we're going to learn about that because those gyroscopes are very useful in everything from GPS satellites to iPhones to navigation systems. So that's a very common tool, but only made possible if we actually spend the time to learn about rotations. And that will be the subject of this part of the course. Hopefully we'll learn about all these things that I've just mentioned here.